Our next speaker is Yelena Guryanova from Institute for Quantum Optics and Quantum Information in Vienna. And Yelena is going to tell us about the resource costs of ideal projective measurements.
Thank you. Can you hear me?
I can, yeah.
Perfect.
I hope.
Okay, so thank you very much for the invitation to speak. I was really looking forward to coming to Bristol because I did all my degrees in Bristol. So I was looking forward to seeing everyone, and unfortunately it wasn't to be. So this is my virtual presentation then about ideal projective measurements and how they have infinite resource costs. So this is in collaboration with Nico Fries and Markus Huber, and we're all at IQOQI Vienna at the Austrian Academy of Sciences. So I'd like to start by looking at two facets or two areas of quantum physics and see what they have to say about the resulting state of a system after you've done some operations or procedures on it. So to begin with, let's revise something we all know, which is that of quantum measurements. A quantum measurement in the most general case is described by a POVM, which is normalized over the POVM elements indexing the outcomes I. We have a rule for the state after the measurement, which is this post-measurement state rho prime, which is normalized in the denominator by the probability of getting the outcome I, obviously. And in the special case that the POVM operator elements satisfy this condition, this pi I should probably be an mi, then we know that the measurement is projective. We say it's projective. Okay, so on the other hand, I'd like to contrast this with a few things that we know from quantum thermodynamics. So in quantum thermodynamics, we have the idea of a global reversible time evolution. So I can take some initial state, rho 0, and I can evolve it with some unitary, which I get from a Hamiltonian. And I know the state of the system to later time. We have also the notion of a thermal state, tau, which is given by the Gibbs distribution. And we know that we know about the emergence of these thermal states through things like entanglement and coarse graining. And one observation that we can make from these two facts is that the unitary orbit of a thermal state is full rank. So thermal states are full rank. So if I evolve them, I get them in full rank again. And this actually implies the third law of thermodynamics, which these people in this paper showed here. So what is the third law? Well, the third law can be thought of as an unattainability principle. It tells you that it's impossible to cool down a system to absolute zero using finite...
Sorry, I need to interrupt you. I'm really sorry. I think your slides aren't scrolling through. We can see kind of the window for your introductory slide, but we haven't seen them scrolling through.
Okay.
Now something has changed.
Do you see the slide now?
Yeah, we can see the thermodynamics from a quantum perspective slide.
Okay, so maybe it doesn't work in, do you see it now?
It's still the thermodynamics from a quantum perspective slide, nothing...
That's okay, that's still right.
Yeah, I just don't know, do you want to try clicking back and forth and see if you can scroll through?
Is that scrolling?
Yeah, looks like it, that's scrolling now.
Okay, maybe I'll leave it like this, maybe it's not working in full screen mode.
Okay, yeah, please, carry on, sorry about that.
No problem. Okay, so we have this idea of global reversible time evolution and the emergence of thermal states. And I just said that the unitary orbit of a thermal state is full rank, which implies the third law. And this tells us that it's impossible to cool down a system to absolute zero with finite resources. And I use the word resources intentionally because you may be using energy as your resource, which we're all used to, but it may be something more like more abstract, like time in the case of Landau erasure. And more recently, people have been thinking about complexity as a resource. So as a theorist, I'm guilty of this myself. When you construct protocols with n particles, which are incredibly complex n-body interactions, which we know are very difficult to implement in the lab. So this kind of complexity can also be seen as a resource. Okay, so we have these two contrasting images then of what a post-interaction state may be. So still thinking of quantum thermodynamics, if I imagine cooling a thermal state from some initial state to a final state, I might do this with a fridge, which is coupled to a target system, either directly via laser cooling or via the bulk, like in a dilution refrigerator. But in both of these cases, what I need to do is I need to invest work so that the target system gets closer to the ground state. And how close it gets to the ground state is limited by the third law of thermodynamics. Now, if we rewind and think about what we know about measurements, if I measure a thermal state, well, I take a measurement apparatus and I couple it to my target system, the system I'm interested in. I choose a measurement basis, so for example, energy, and I obtain the outcome I, or EI, with some probability given by a coefficient from the Gibbs distribution. And the question is here, what is the final state of this process limited by? And it appears to be limited by nothing. But if we think more closely about it, what these two pictures are telling us are two very confusing things, because on the left-hand side, I have a picture which tells me that I can't cool something down to the ground state, which in non-degenerate cases is a pure state. Whereas on the right-hand side, I have this picture which tells me I just need to measure something and I project automatically into the pure state. So by now, I guess you've all realized that I did my PhD with Sandro Popescu, because how can you start a talk without a paradox or a contradiction? So the point of this work was to show, of course, that there is no contradiction. We know that in the lab you can do finite time and finite energy measurements, but we also know in the lab that these measurements are prone to small errors, for instance, dark counts in photon detectors and things like this. And what this really means is that the state of your system after your measurement is never truly pure. So this is the outline of my talk then. I'm going to describe what a quantum measurement is in the most kind of basic way, with a description and definition. I'll then talk about an ideal measurement and motivate this with 3 mathematical properties. And then later we'll move on to the results to show that ideal measurements aren't possible. But of course, approximations to them always are. And we can quantify the energetic cost of making a non-ideal measurement. And I'll conclude with some summary and some future work. Okay, so what is a measurement in the most fundamental sense? A measurement is something that takes a system and a pointer. It couples them, they're initially uncorrelated, and it correlates them in such a way to get this final state rho s prime. So in this picture, this brown circle is my system and this bigger square thing is my pointer. And at this point, I should say I have a disclaimer, and the disclaimer is that this talk is not about how a measurement, it's not about collapse theories or why a measurement occurs or an outcome occurs or how I observe something. So in this talk, the word measurement will be taken to mean this arrow here. So the map going from the system pointer and correlating them, plus statements I can make about this post-interaction object. So that will be my definition of measurement here. Okay, so I take these two things, I couple them, I interact them, and I get something correlated. Now, imagine I'm measuring a qubit. Well, I need to assign states of the qubit to states of the pointer. So maybe your pointer is a really big magnet with lots of spins in it. Then you assign some object, pi naught, to some collection of spins which you take to mean the state of the system being in the state 0. And this object, for instance, pi naught, can correspond to many microstates of the system. So for instance, if half the spins are up, this can correspond to many different microstates, which you still interpret to mean that the system is in the states up. Okay, so you divide conceptually your pointer Hilbert space into these 2 parts if you're measuring a qubit. And what you want from your measurement is that when you observe the pointer, whatever that means, that if you observe one of these microstates corresponding to this operator you defined, then you can infer unambiguously that the state of the system before you interacted them was also in the state up. Similarly, if you see the pointer telling you down or indicating 1 on some dial, then you know that the state of the system before the interaction was 1. In the ideal case, what we want to do is we want to impose a few more constraints mathematically. So we say that an ideal measurement satisfies 3 fundamental properties. These are those of being unbiased, faithful, and non-invasive, which I'll explain now. The idea of being unbiased is that the pointer and the system statistics are the same. So if you have a system which is in a mixed state, a quarter of the time up and 3/4 down, then your pointer better show you the same statistics when you measure over and over again. Your ideal measurement interaction should be faithful, which means that the probability of your guess is correct. So it means you can interpret this as meaning that the pointer never shows you the wrong outcome. When it shows you 1, you know that the system is in 1. When it shows you 0, you know the system is in 0. And the last property is this idea of being non-invasive. So in the measurement basis that you choose, for example, energy, the system is not disturbed on the diagonal. So maybe your measurement process swallows up coherences, but you can keep measuring the system again and again and getting the same statistics. And these intuitions can be formulated mathematically. I won't go into details here, but I'd like to focus on this idea of being faithful. So faithful is captured by this function C. C is, you can think of this as the correlation. How well is the system and the pointer correlated? If the answer is 1, the system and the pointer are perfectly correlated, and your pointer never tells you the wrong outcome. So to illustrate this, you can think of an example. So imagine your measurement leaves your system and pointer in the state 0, 0. So this is clearly a pure, classically correlated product state, but it has perfect correlation. The measurement that resulted in this state is said to be faithful. That is because when I look at the pointer in the state 0, I know for sure, without an ambiguity and with probability 1, that the state of my system was also in 0. And what you can do then is you can mathematically formulate this idea of the ideal post-interaction state. It's not terribly important to understand this, but it's something that's block diagonal. And it motivates this definition of being faithful because your measurement is faithful so that the correlations are equal to 1 if and only if you have this ideal post-interaction state. Okay, good. So let's do a really quick example of an ideal measurement of a qubit system by 1 qubit pointer. Here's a system, here's a pointer. I chose a diagonal system, coefficients AB. I didn't have to, I could have put some coherences, but I was lazy. And I've chosen this pointer in the pure state, in the ground state 0. So that's clearly this matrix here. And what I do is I apply a C naught, and I get this other post-interaction state rho tilde. And one can check from the mathematical constraints that this interaction, or this measurement, was unbiased, faithful, and non-invasive. And in fact, you can go one step further. You can say, you can do this with a system of any size. So I still take my pointer in a pure ground state. It can still be a qubit. And I can take a system of any size, any dimension, any coefficients, whatever, and I apply the generalized UC naught, the generalized C naught gate, defined here. And I can check all of these properties, and I find I'm done. So, okay, that's great. So I can measure any system perfectly according to the definitions. But the point is I did this with a pointer that's in the pure state. And we'll see that this is the problem here. So we say that a measurement is non-ideal if any one of these 3 properties fails to hold. The property of unbiasedness, this idea of the system statistics, the property of being faithful, which is when you have perfect correlations, and this idea of being non-invasive, which is that you don't disturb the system. And one of the results then of our paper is this theorem. One of the results is to say that ideal measurements are not possible. So faithful measurements, or perfect correlations, this idea that your pointer never makes a mistake, are only possible if and only if one can prepare pure states. By the third law of thermodynamics, you cannot prepare pure states. Therefore, faithful measurements are not possible. And ideal measurements, where you have to satisfy all 3 things in this triangle, are not physically feasible. And the fact that pure states are not possible to create is evidenced by a huge body of work. So creating pure states costs infinite energy, takes infinite time, requires infinite particles, which is the same as I mentioned, and things like this. So there's been an abundance of literature on this. Okay, so how do we move on? So what we want to do is we want to approximate ideal measurements. What we saw is that via the definitions, we had these 3 properties. And what I didn't mention was that these properties are pairwise related. So for instance, these 2 properties imply this one, these 2 imply this one, and these 2, up to a caveat I won't go into, imply the last one. So as soon as one of them goes, the whole triangle collapses and we no longer have an ideal measurement. So since ideal measurements are not possible, what we want to do is to determine how closely they can be approximated. So we've lost this property of being faithful, but the other two we can salvage. So what we learned from the fact that pure states, you cannot call something, pure states don't exist essentially, is that the initial pointer state must be full rank to avoid self-referential descriptions of measurements which rely on pure states. So if you have a pointer which is not full rank, what that means is you've somehow projected onto a non-trivial subspace of the pointer. So you've somehow done a projective measurement, which is the same as having a pure state on this subspace. So what's a good candidate for a full rank state? Well, for us, a good candidate was the thermal state. So that's the thermal state of a qubit given with inverse temperature beta. And why is this a good candidate for a pointer state? Well, when you go in the lab, typically things are thermalized either to the temperature of the lab, or maybe you've cooled it down to some temperature, but typically they're stable. So they're in some thermal equilibrium before you start your experiment. Okay, and now we have a choice. So we can't have perfect correlations, so we have to accept that our pointer will always make a mistake. But what we can do is engineer an interaction that is at least unbiased. That is the minimum we require of the interaction. So before we had a situation where we had a system and a pointer, we coupled them and we got some correlated state. And now we've argued that this pointer must be in a thermal state and must be full rank. And this interaction, this arrow, we will take to be some unitary, which has the property of being unbiased. It preserves the statistics between the system to the pointer. And I've chosen unitaries. I mean, in general, this arrow can be any map, but I've chosen unitary because in the end, I want to account for the energy of this process. And I can do that with unitaries because if I choose CP-TP maps, I have to bring in ancillas and account for the work invested there, and I can also embezzle energy as well. So that's what I want to do. So the goal is to bring this post-interaction state, which we achieve via unitary, as close as possible to the ideal post-interaction state. This thing I flashed up earlier in block diagonal form. What we know is that pure states make the best pointers. Because we saw that with the U0, for example, that the pure state is the best. So what we do is we conceptually split this total unitary into two parts, a cooling part and a correlating part. We want to cool the pointer in the beginning to bring it closer to a pure state, and then we want to correlate the pointer in the system as much as possible to actually affect the measurement. So in point one, the cooling part, what I actually want to do is I want to lower the entropy of the pointer via a rank non-increasing map. That's the precise thing that I want to do, but what I will do is I will just use a quantum refrigerator because that is well understood and quantifiable, and there are many results on this. So these two parts will be my total unitary, and this is the schematic of what I'm going to do. So here's the system, rho S, and I'm conceptually splitting the pointer into two parts. So imagine the pointer is composed of 2n particles. Half of them are now going to be this 1 qubit fridge, and half of them are going to be the pointer. So these fridge particles are going to cool the pointer particles to some new temperature, beta 0, this new inverse temperature. And then I'm going to apply a correlating unitary between the system and the remaining pointer particles. So this combination of U cool and U core is the total unitary. Okay, and I can compute the energy of these things via the normal way, and I can account for the energy as the sum of the two parts of the unitary that I apply. So first I cool, and in our paper we use this 1 qubit fridge, which is an exhaustive work of all possible fridges you can have, I think, by these people here. And they have a very, they have an analytic expression for the amount of energy it costs to cool a pointer. So if you start with some thermal pointer of n particles, at temperature, inverse temperature beta, you can cool that to a new temperature given by, which is a function of the gaps in your fridge and your pointer. And you can see clearly here that as I cool towards the ground state, which is beta is infinity, this cooling term will diverge. In the second step, I want to correlate the system and the pointer to generate as much correlation as possible. And what we show in the paper is that, oh no, it's gone. Okay. What we show in the paper is that there is, we have an analytic expression for the correlating part. This analytic expression, essentially, it's a minimization, an optimization problem. You want to minimize the energy you spend cooling such that the correlating unitary is unbiased. And you want to do this to the maximum possible correlations. What are the maximal possible correlations? Well, that's given by the first n/2 Gibbs distribution coefficients. So this is a nice thing that points up another divergence that occurs. So what I can do is I can either call my pointer to the ground state, so that means taking the limit to beta is infinity, and I get perfect correlation. And it doesn't matter how many pointer particles I have. The other thing I can do is I can take an infinitely large pointer, say 20, 100, 1,000 particles, and that will also give me perfect correlation in the limit. So it's another example of this divergence showing up. So the final slide I want to show you then, or one of the final slides, is this cost of an ideal measurement. So in this schematic, what we have is an example of a system with 1 qubit, a pointer with 6 qubits, and some realistic energy gap between them. And the idea is that we start at room temperature and cool the pointer with some fridge, and then we correlate at the new temperature. So if I look here at this 0.9, in order to get correlations 0.9, I need to invest this much energy, roughly 100, into cooling the pointer, and a tiny amount of energy, which is given by this inset here, into correlating the pointer. Note that this function is always finite. And as I approach perfect correlation, you can see that this cooling cost diverges infinitely. What's important is that it's really tight. So the reason we have really good measurements is because this curve is so steep. So in summary then, we have a theorem. The theorem is that unbiased measurements, the ones that system and pointer statistics are the same, can always be implemented at finite cost and in finite time. The corollary of this, however, is that to be faithful, the perfect correlation, so the pointer never makes a mistake, the pointer has to be cooled, and that's subject to the laws of thermodynamics. And as a consequence, we see that obtaining reliable knowledge about quantum systems generally requires macroscopic quantities of work, so that perfect knowledge is infinitely expensive. And although I presented results on, I showed you results about qubits and things, actually the whole recipe is valid for any system and any pointer Hamiltonians at all. So with that, I conclude that pure states are not for free. I'll skip the further work, and thank you for your attention.
Great. Thanks, Yelena. Clapping for the 250 or so participants in the channel. We've got time for one question or two. I've got one.
Yep.
You mentioned earlier in the talk and just at the end there that your analysis is general. Yep. You mentioned optics and dark counts and that kinds of things. I mean, the language, the thermodynamics language that you're using of heat baths and stuff is a little bit foreign to the quantum optics idea of projecting into one of two modes or something. Can you make that translation for us a little bit clearer?
Yeah, this is quite subtle. So, okay, so suppose that you have send a photon. Okay, so you can argue that you can have an optics experiment where you have a near perfect beam splitter, and you send single photons and you count the clicks in your detectors. So you know that none of the photons have escaped, and you know that you've done a measurement, and you claim that you've done a projective measurement because you've heralded the photons at your detectors. So depending on which detector clicks, you can say that the polarization was either horizontal or vertical, fine, but you've destroyed the photon when you've made this measurement. So how do you prove to me that the polarization was actually horizontal or it was actually vertical? Okay, then you say, after my polarizing beam splitter, I'm going to put some, polarizing beam splitter, I'm going to put some polarizers, horizontal and vertical, into each arms of the thing, of the interferometer. So I know for sure that, that the photons that arrive in the detectors are horizontally and vertically polarized. But again, when they arrive, you've destroyed the photon. The detection destroys the photon. So you can never prove that something was perfectly aligned, or a horizontal photon didn't slip through into a vertical path and things like this. That would be what I would do.
Right. That's the end of our time. And there's a message on Slack from John Rarity saying, perfect talk, infinite energy.
Thank you, John.
There you go. No small praise. Thanks a lot, Yelena.